let's talk about all the different kinds of light, okay? And because light can have any wavelength, okay? Light can have any wavelength at all. It can have microscopic, tiny little wavelengths that you wouldn't be able to see if you even if you could see the actual up and down motion. If you drew it, it'd be too small to see. And the wavelength of light could be bigger than our planet. It could be hundreds of kilometers. Any wavelength is possible with light. And because that's a lot of wavelengths, what we usually do is we classify light based on how big its wavelength is, okay? And we divide light into 7 categories, or 7 types of light, based on how big the wavelength is. But technically, if we're classifying light based on how big its wavelength is, what other 2 things are we technically also organizing these things based on? If we're classifying light based on wavelength, what other 2 things are we classifying light based on? Don't overthink this. What other 2 things are directly related to wavelength? Oh, and sorry if you're British. I think this is a bad sign in England. Oh, you guys don't want to take a guess? Okay, I'll give you one of them. Okay, I'll give you one of them. If you're classifying light based on wavelength, that means you're also classifying light based on frequency. Oh, and there you go. There's the other one. Energy. So these classifications, the types of light, are organized according to wavelength, but that means they're also classified based on frequency and energy, because those 3 things all are directly related to each other. Okay? So, here we go. Good job, guys. Now, here we go. So, here's my next question. The first type of light that ever was discovered by humans. Does anybody know what kind of light was the very first kind of light that we've discovered? Okay, what was the very first kind of light we ever knew about as human beings? Sunlight is on the right track. Sunlight is on the right track. Let me put it this way. What kind of light do we see out of the sun? Oh, somebody got it. Visible light, okay? Which sunlight, the sun produces a lot of visible light. The very first kind of light we ever discovered is called visible light. And how do we discover it? By seeing it, right? Here's the next question. Why was visible light the first kind of light we ever discovered? Why didn't we discover some of the other kind of light first? Why visible light first? Why not the other stuff? What's true about all the other kinds of light? Think you guys are getting it? Yeah, that's basically it. Visible light, by definition, is the light that we can see, right? So all of the other kinds of light are invisible to us, all right? So we didn't even know they existed, so that's why we couldn't find them yet, right? So let's talk about this. Okay, so visible light. We're going to write that down in a second. But we need to figure out where it's going to be in all of the different categories, because we're going to put them in order of wavelength. So visible light. Would we expect visible light to be an extremely large wavelength or a very small wavelength? Would we expect visible light to have a very big wavelength or a very small wavelength? And don't worry if you get this wrong. It's totally fine. Because this one, it's not something you typically think about. And usually I get, small, middle, big, large, tiny. You're probably getting all kinds of guesses there. That's okay. Let's figure it out. The things we're looking at can be pretty big, right? But the size of the thing you're looking at is not the same thing as the size of the wavelength of light it's giving off. Let's think about this. Don't overthink this. what part of your body does the light have to enter in order for you to see it? In order for you to see the visible light, what part of your body does it have to enter? Yeah, it's got to go in your eyes. And not only that, it has to be able to fit in the pupil, right? It's got to fit inside the little dot, the little hole on the front of your eye. And that means that in order for visible light to stay coherent on the way to your body, it needs to have a wavelength that can fit inside the hole in the front of your eyes. So that right off the bat is saying that it can't be bigger than this, because if the wavelength was bigger than that, it would get disrupted on the way into your eye, and it would lose all of the image it was trying to send you. So it's got to be that big. But here's the thing. You don't see something right when the light enters your eye. You actually see it when it enters your retina. Specifically, when it enters the cells of the retina. Don't worry about the word retina. This is not an anatomy class or anything. It's just the fancy word for the back of your eye, like a piece of the back of your eye. But here's the thing. That means that the wavelength of visible light needs to be small enough to enter at a single cell of the human body. So what kind of sizes are we talking about for visible light? What kind of sizes are we talking about? Big, small, medium? If it's got to be able to enter a single cell, what's its size going to have to be like? Small, right? Not just small, but very small, okay? So it turns out that visible light, the wavelength of visible light, is measured in nanometers. That's why I actually brought up nanometers back at the beginning of this lecture, because nanometers are very, very small. That's what we use to measure visible light wavelengths, okay? That said, we consider visible light to be the middle category, okay? The middle category is already pretty small. So what I'm going to do is I'm going to write visible light right here. But if you're writing this in your notes, make sure, like me, you're leaving a lot of space to the left and the right of visible light. Because we're going to list 3 categories over here on the left, and we're going to list 3 other categories over here on the right, okay? And the way we're doing this, we're doing it in terms of increasing wavelength in this direction. Okay? So this would be the smallest wavelength. And over here, we're going to have the longest wavelength. Okay, so the shortest wavelength or smallest wavelength over here, the longest wavelength on this side. Okay, we're not going to do all the categories today, but let's just zoom back in on visible light and put some little vertical lines right here. Specifically, visible light is any light between 400 nanometers and 700 nanometers. Oh, and it froze on me again. Man, I hate this thing. Okay, so 400 nanometers to 700 nanometers. Those are both in M, okay? And even though 400 and 700 sound like big numbers, that's 400 of a tiny, tiny little nanometer, okay? Now, here's my next question about visible light. Is there any way for the human eye to tell the difference between different wavelengths, to tell the difference between a 400 nanometer light and a 700 nanometer light? Is there any way, yes or no, for the human eye to tell? Turns out there is. Turns out there is. And somebody actually just said it. The way that we tell the difference between different wavelengths is different colors. Okay? So light that has a wavelength of 400 nanometers is a different color than light that's 700 nanometers. Okay? Different colors. All right? Now, do any of you happen to know which color is the absolute longest that we can possibly see? Does anybody happen to know what color that is? 700 nanometers. What color is that? Any guesses? Give me some guesses. What color is the longest color that we can see? Red. That's actually, I'll just go with that. Good guess, guys. That is correct. This is red light. I'll just put a capital R right there. 700 nanometers is red. It's the longest color that we can see. If it's any longer than red light, it's invisible. If it's over here, it's invisible. Okay? Okay, on the other side, 400 nanometers, the shortest color we can see. Does any of you guys know what color is the shortest possible color we can see, the 400 nanometer side? Yeah. It's purple or violet, right? Violet or purple. I'm going to use violet because that's typically what we usually call it. But yeah, it's basically purple. So violet is the shortest color we can see. Red is the longest color we can see. Okay? And every other color is somewhere in between there, right? Next to red, a little bit shorter than red is orange. A little bit shorter than that is yellow. The kind of right in the middle of the visible range is green. Green is right in the middle between 400 and 700. And then you got blue. And then you've got indigo. And then violet. Have you ever seen this order of colors before? Red, orange, yellow, green, blue, indigo, violet. Where have you seen this order of colors before? Yeah. So, it's the rainbow, right? That's the rainbow right there. So it turns out that rainbows are not just random. There's a reason that rainbows always come out in this order. Okay, sometimes little kids will draw a rainbow in another order, and then somebody will say, if they're being a big jerk, that rainbow's all wrong. Don't be a jerk to a little kid. But technically it is wrong, because if you don't put them in this order, you don't actually have a real rainbow, right? Because it turns out, check it out, let's see if we can figure this out, rainbows are organized according to what? What are rainbows organized according to? Based on what we're saying over here. Rainbows are organized according to what property? That we've already talked about a lot today. Wavelength. That's correct. Rainbows are organized according to the size of their wavelength. Okay? Basically, all of the light in the rainbow is split into all of its different wavelengths. and they're organized according to how big that wavelength is. I'll talk a little bit more about that in a second. Actually, you know what? We'll talk about it right now. How does that work? Well, it's basically like this. I have a picture right here. Here we go. Here's a picture from the book, chapter 5, the one we're in. And you probably have seen something that looks like this before if you've ever seen that Pink Floyd album. Dark Side of the Moon, I believe, is that Pink Floyd album. Wait, is that one? Yeah, anyway, whatever. Don't worry about Pink Floyd. But right here, what do we got? What color is this light right here? What color is this light? What color is this light right here? Yeah, that's white light. And we talked about this a little while back. White light is actually a combination of all the colors. So what we can say is that white light is actually just a combination of all of the visible light colors mixed together. Okay? But check this out. If we go back here, when this light enters this glass, it bends, right? When this light enters this glass, it bends. Do you guys remember what that's called? Do you guys remember what that's called? Starts with an R. What is that? What do we call it when light bends when it goes through a new substance? What is that called? Yeah, that's refraction. Now remember we said that different colors bend different amounts in refraction? Which color did we say bent the least? Which color bends the least in refraction? And thus is able to get through things a little bit easier. Red, right? Red bends the least, okay? And on the other hand, we said that blue and violet bend the most. So if we look, and every other color bends something in between. So in this picture, this white light contains all the colors, but as it goes through, red bent to here, violet bent more. So see how it ends up bending farther over to the side. Violet's way over here. And every other color is bending in between in order. Check it out. Red bends the least, then orange, then yellow, and then eventually violet. So, here we go. If we put this all together, what property of light determines how much it bends? What property of light determines how much it bends? If different colors bend different amounts, what do we say that these colors represent? Wavelength. Okay? And let's put this together one more time. If wavelength is what determines how much light is going to bend, and we know that red bends the most and violet bends the least, then what kind of wavelengths bend more? Shorter wavelengths or longer wavelengths? Shorter wavelengths bend more or longer wavelengths bend more? Remember, red bends the least. Shorter. And it turns out that works even for invisible light. Shorter wavelengths bend more, okay? It's your wavelength that determines how much you bend, and the longer your wavelength is, the less you bend. The shorter your wavelength is, the more you bend. And real quick, when do we see rainbows? After it rains, right? So A rainbow is caused by this exact same thing. Rainbows are caused by refraction. The light in the rainbow comes from the sun. But there's not a bunch of little pieces of glass in the air. So what is in the air after it rains that could act like this little piece of glass to split the sunlight into a rainbow? What causes the light to refract after it rains? What do we have all over the air? It's not nearly as much of most of the time. Water. Essentially, little droplets of water can act just like this piece of glass here, so that when you pass light through those droplets of water, you end up refracting it into a rainbow, okay? And that's also why you can make a rainbow with like a hose, right? If you've got a hose, you're spraying a hose on a shiny, sunny day, you could probably see that rainbow around it. That's refraction also, okay? It's just refracting through your hose water instead of the sky water, all right?